Hello, good morning. Welcome to PyCon. Welcome to my talk about the hidden costs of your favorite functions. I want to introduce myself. My name is Gershovitz Bar. I'm a software engineer at Meta. I write a tech blog called Maya's Algorithms in English, and it's really cool. You should check it out. If you don't know it, that was a very shameless self-promotion. And I really love Python. I've been working in the industry for a little above 10 years now, and 5 of those I worked mainly in Python. And even though I don't today, I still really like it. It's so easy. Every time I need to do something quick and easy, quick and dirty, something for a personal project or for friends, you can't go wrong with Python. I especially love how elegant and short it is, mainly the one-liners, which is sort of what I want to talk about today. So, what am I gonna talk about? In the next 20 minutes, I'm gonna try to answer the age-old question of what to do when your code is slow. I'm gonna try to give you some tools that have worked for me in the past, and mainly a methodology about how can you approach this really serious problem to come and solve it. I wanna apologize in advance if my voice breaks a little. I'm really nervous, but I know that together we can do it and we can make it through. So let's start with Stack Overflow. We all do it. Well, I do it, none of you guys do it, but I know that when I need to solve something new, I go and copy some other code and I tinker with it and change it a little bit until it works and solves my problem. I always make sure it works. I always test it. I'm very good with testing, but I don't always check how it works and why and how it's implemented. So my advice for me and for anyone else is examine your code closely. Look behind the scene. Look how it's implemented. The difference in implementations means it's either slow or quick, complicated or very simple, linear complexity, or, God forbid, exponential complexity. As a case study, I want to talk about Pop. Oh, not this Pop, although she's great. Yeah, this Pop, much better. This seemingly very innocent library function, Python library function written in cython, which receives a vector and retrieves a single item from the start of it. It feels like it should be constant complexity, like retrieving an item from an index. But alas, it is not. It is linear complexity. If you look into the implementation of Pop in Cython, which I have, you discover this really unexpected implementation where to pop an item from the list, you remove that single item, and then you shift left the entire rest of the list, each and every item, which means that for removing the first item, you need to shift the entire list, thus getting linear complexity. That means, by the same logic, that if you remove the last item of the list, you get constant complexity. And I want you to remember this because I'm gonna get back to it in a little bit. Now I've got lights, I feel so important. Okay, so why am I even talking about complexity? Well, it is a university, but we are not in university. It's been a while since algorithmic classes in science, computer science, and it might not seem very important to talk about linear, constant, exponential complexity. Well, my mom, which was a programmer in the 70s, used to tell me horror stories about if they written code that was too complex, too heavy, or heaven forbid, had an endless loop. The computers would get overheated and burst into flames. I'm not sure that's true, but it did give me nightmares about writing endless loops, and I haven't since. And today, this is not the case. Our computers are strong. We have seemingly infinite computational power, which we can do anything we want with. We have a lot of distribution power and options. So why is it important how good and performant our code is? Well, the answer is really simple. It's data. We have huge amounts of data. We have more and more each day, and the amounts of we couldn't even imagine 5 or 10 years ago. And when you're working, like much of us are, when you are working with these huge amounts of data, even a small difference in performance can be really meaningful when it comes to production, to real life data that grows bigger by the day. So I want to emphasize this difference with a little story. This is a personal story about something from a company I've worked in a couple of years ago. It's a story about a procedure, a main procedure in the company that ran for all of our customers. And it ran for most of our customers for an hour, 2 hours, 5 hours tops. But for one customer, the biggest, most important customer, it ran for 25 hours. Yes, that's correct. It was a daily function that took more than a day to finish, which means that this very important customer never had updated data. It's such a lovely, lovely state to be in. So I got the lovely task of getting to figure out what happened and how we can improve the performance of this procedure. Well, I took this procedure, I ran it on my machine, and it worked. I tried to stress test it. It was pretty quick. I got an hour, 2 hours, but I never got to the same kind of heavy running time we got in production. It was a very complicated procedure with a lot of I/O operations, which are really heavy, and a lot of tasks and subtasks. And it was really hard to follow, and I tried to look into every line, figure it out, and improve the performance, and I couldn't. And I got an advice from a colleague, which is what you do in these cases. And he told me about something I wasn't familiar with before, called a profiler. In case you don't know, like I didn't, what a profiler is a tool for Python, in this case, which runs along with your code and measures important metrics about your code, like how long is it running for, and specifically how long is everything running for. There are a lot of different kinds of profilers you can choose from, or even use a couple. But from what I've seen, the main metrics these profilers are measuring are the amount of time spent on each action, line or function, and the number of times each function runs. Why is this important? Well, the amount of time is super important. It can help you identify bottlenecks, see what is taking up most of your time. Maybe it won't be what you expected. It can give you real data. And the second one is also really important because it can help you discover bugs, maybe help you discover some things that is happening more than once. So super important, super useful, and I did use it to discover my bottlenecks, and it did improve the code. So I wanted to run a little example for you. I used this tracer, which is a profiler that I found recommended, but again, there are a lot of them. And I ran it with this very simple function that I wrote. I got a list, and I deleted it one item at a time, one from the start and one from the end. Remember, I told you we're going to talk about the pops, pop 0, pop n. This is what I did. And this is this little screenshot of the report this tracer is going to give you. You can see In the top half, you have a nice visual report. You can see the pink ones are removed from the end, and the tiny little bit blue ones is the other way around. The pink ones are removed from the start, the little tiny blue ones are removed from the end. You can see visually how much more small it is. And beneath, you are getting a textual report. So let's see what were the results of my experiment. Well, for a list which was 100,000 items long, it took me 20 microseconds to remove, on average, to remove items from the start of the list. And it took me 0.8 microseconds to remove from the end. This is a very impressive difference. It's 20, 25 times over removing from the end. And I thought this was really impressive, but I got to thinking. We know that the complexity of remove from the start is linear, which means that this difference, impressive as it might be, will not remain constant. If the list grows longer, so will the difference. So I ran the experiment again. This time with 1 million items. I said I'm nervous. I ran the experiment again with 1 million items. This time, removing from the start on average took me 62 microseconds, and removing from the end took 0.6 microseconds. That is more than 100 times over. It's much, much worse than the 20 times over we had before, and it's only gonna get worse the longer your list is. So I thought this was a very interesting example for this phenomenon. But I also know that you really didn't come here to hear about pops, as fun as they may be. And I wanted to give you more of a kind of real life, interesting example that you might work with every day. So I was not surprised to see that me talking about pandas. Pandas is a very useful, powerful library for working on large data sets in Python. If someone doesn't know it, it's really cool. It has a lot of features. It's not always the quickest, but it can be. I remember when I worked a lot with pandas, that sometimes I had many different ways to achieve the same thing, to do the same thing. And it was hard for me because I didn't know which option I should choose, which implementation, if they all do the same thing. And I thought it was an interesting opportunity to maybe compare and contrast, maybe to see if there's a performance difference between all of these methods. So I wanted to compare between 3 ways of doing things the pandas way. I've written a little function, and I wanted to use it to add another series to a data set using 3 ways. Iteros, which is like a normal Pythonic loop almost. Apply lambda, which gets a function and applies it to all of the rows, pretty good. And vectorization, which actually works on series instead of rows. And let's see my data set. Yes. My data set was Elon Musk 2020 tweets. He had 11,717 of those. It felt a lot more, but I swear that's all there is. And I had 36 columns in my data set. And I devised a very scientific rating system for his tweets, saying any tweet that has below 50 likes is a low tweet. Any tweet between 50 and 500 likes is a medium-liked tweet. And every tweet with more than 500 likes is a very high-liked tweet. This means nothing. He has 98 million followers. Don't compare it to yourselves. But this is what I wanted to run. So I wrote this function and I ran it the 3 ways that I've shown before, with iteros, with apply, and with vectorization. I assume you can guess the results, but let's see them nonetheless. Iteros for this data set took 478 milliseconds. Apply took 110 milliseconds. And vectorization took 2 milliseconds. That's amazing. More than 200 times better than iteros. So I know what I'll be using the next time I use pandas, and it's a good example to how you can test and make sure your implementation is the best that it can be. And that leads me to my last point of this talk. Monitoring. Well, it's quite the opposite of everything I said so far, but there's a very important point I want you to take with you, and that is that your code is not going to be perfect. You should look into it. You should look at the implementation. You should research it. You should improve it. You should do the best you can to make it really good and quick and performant. But it's never going to be perfect. And at some point, you need to say, okay, we did the best we can. It's going to go to production now. Usually when the product manager say it, but you can say it before. So do yourself a favor. Don't over-engineer your code. Don't make it as future-proof as possible. I know it sounds insane, but it's not. It can be a waste of time trying to make it perfecter than perfect. But Maya, what can we do? You said that our codes need to be performant and quick, and we have so much data, and what about your 25 hours function? Well, monitoring can help you there. Monitoring can tell you if your code is good enough in production, in actual real data usage. So, are you doing your monitoring right? How can you know what monitoring needs to give you? Well, if you don't only think on monitoring in terms of waking up in the middle of the night to fix things, and if you think about monitoring as something that will help you fix and improve your code along the way, you can see that you need 3 things. You need to catch changes as they emerge. The moment your data changes and grows, you need to know about it before your customers know about it. The second thing is that you need to have good access to comparison data. Have your retention large enough and long enough so you can see what happened, what changed, and see on what data your function ran smoothly and quickly, and when it ran really slow. And the third one is really important. You need to identify patterns. You need to have enough metrics, enough logs, and enough data to see what is causing problems. When you have that, you just monitor and repeat. You improve when you need to. So, remember this. If your code is suffering from bad performance, there is something you can do. You can examine your functions closely, see how they operate, see how they're implemented. You can get a full profile. There are tools. You can time it. You can see how many times things are happening and how long they're taking to help you identify bottlenecks. And when you're ready to let that code go, you need to monitor it and keep improving it for the entire life cycle. And you will be good to go. Thank you so much for listening. Well, time-wise, I think I'm finished, but there's no responsible adult here to tell me if I need to take questions. So, oh, hi. One question? Okay. If anyone has a question. Oh, how did I choose to show you vtracer? Well, as I said, there are a lot of popular profilers, and I actually think you should use multiple on your codes because they're going to give you different metrics. I use vtracer because I found a couple of articles talking about how good he is, and he has a nice visual effect that I thought it really shows. And yeah, thanks.